There are two types of stereoisomerism, diastereomerism and enantiomerism. If you were to look at all of the known organic molecules that contain tetrahedral stereocenters and graph on a pie chart enantiomeric and diastereomeric relationships, the result would look something like this. The vast majority of molecules related as stereoisomers would be diastereomers, and a much smaller subset, namely the subset that are mirror images of each other, would be enantiomers. In this respect, diastereomerism is more common than enantiomerism, which is one reason it's important to study. Another reason is that diastereomers are more different than enantiomers. In other words, differences in physical properties and reactivity between diastereomers are more extreme than those between enantiomers for reasons that will become clear when we talk about the energetics of stereoisomerism. Molecules that are related as diastereomers are stereoisomers that are not mirror images. It's that simple. They're defined by what they're not more than they're defined by what they are. And the reason identifying them as not mirror images is important is because it logically tells us that the internal distances between atoms in the two structures must differ. This means that the two molecules have different energies, and we'll explore the implications of this in a later video in this series. Just to prove to you that diastereomers have different internal distances, here's an example of diastereomerism involving an alkene. Switching the positions of the B and H2 groups converts from the trans isomer that we're seeing here to the cis isomer that we see on the right. And just to model these two molecules, I've replaced A and B with methyl groups. The molecule on the left is trans-2-butene, and the molecule on the right is cis-2-butene. By internal distances, we just mean the distances between corresponding atoms within the molecules. For example, the two outer methyl groups are corresponding groups in these two structures. If we ignore their three-dimensional positions, they're in the same spots in the two molecules. But the distances between the methyl groups in the two molecules are different. Here we can actually measure the distance as about 0.384 nanometers. In the cis isomer, they're much closer to each other, 0.282 nanometers. This suggests differences in steric repulsion, for example, suggesting that the energies of the molecules are different. This difference alone is enough for us to come to this conclusion, but I'll leave it up to you to explore some of the other internal distances in these molecules to verify that they are indeed different. Here's another example of diastereomerism involving only tetrahedral stereocenters. If we exchange the hydroxyl group and implied hydrogen on a dash at the starred carbon, we end up with a molecule that is a diastereomer of the original. They're not mirror images, and we can verify this by lining up the molecules to try to make them mirror images. If, for example, we rotate this molecule on the left this way and try to rotate this molecule so that this hydroxyl corresponds with this hydroxyl right here in the front, and we see that although those carbons look like they're looking in a mirror at each other, the back carbons are having problems since this hydroxyl is pointed away from the mirror in the right-hand molecule, but this hydroxyl is pointed towards the hypothetical mirror in the middle here in the left-hand molecule. So these are not mirror images. However, they're also not the same, since based on this switch that we made, we know that they differ in configuration at the indicated stereocenter. They're diastereomers, and like the trans and cis-butene case we looked at the beginning of this video, they have different internal distances between their groups. The big place where this occurs is at the hydroxyls. Notice here that the hydroxyls are much closer together in the molecule on the left, 0.262 nanometers, while they're much farther apart in the molecule on the right, 0.358 nanometers. That difference between these internal distances suggests differences in both physical and chemical properties between these two diastereomeric molecules. So far, to identify diastereomeric relationships, we've verified that the molecules are stereoisomers, in other words, they have the same connectivity and same molecular formula, and verified that they're not mirror images by lining them up as if they're looking in a mirror at each other and verifying that one is not the mirror image of the other. There's a shortcut you can use to identify a diastereomeric relationship between two molecules that contain only tetrahedral stereocenters. And this uses the idea that diastereomers differ in some configurations, but not all configurations of their tetrahedral stereocenters. After we look at enantiomers in the next video, we'll clarify why this works. If we look, for example, at these two molecules, we should notice that the molecules have two stereocenters apiece, the two methyl-bearing carbons. And in analyzing these structures to see whether they're the same or different, we should notice that these stereocenters correspond to each other in the two structures. We can assign a configuration to each stereocenter to determine whether the molecules are the same or different. I'll leave the details up to you, but the stereocenter on the left has an R configuration in both molecules, in fact. In the left-hand molecule, this stereocenter has the S configuration. But in the molecule on the right, this stereocenter has the R configuration. Now that we've done this analysis, we can see that the molecules are the same at some of their configurations, namely 1, but not all of them, since they differ in configuration here. As a consequence, we can conclude that these two molecules are diastereomers. If you're more comfortable assigning R and S configurations rather than rotating the molecules as a whole and verifying that they're not mirror images, this can be a more straightforward method to determining whether a pair of molecules are diastereomers or enantiomers. Here are the cis and trans pentane diols from the last slide. Applying the same method, we find that the stereocenters on the left differ in configuration. The left-hand one is R and the right-hand one is S, while they match in configuration at the other stereocenter. Both of these have the S configuration. Because they match in configuration at some of their stereocenters, but differ in configuration at others, these two molecules are also related as diastereomers. In the next video, we'll take a more detailed look at the other type of stereoisomeric relationship, enantiomerism.